Good morning, everyone. I'm Kong Huimin from China Institute of Disaster Prevention and Technology. Our team members include Professor Gu from Nanjing University of Technology and Dr. Wei from Göttingen University of Germany. The title of our presentation is Numerical Simulation of Pre-Seismic and Coseismic Continuous Response of Water Level, a case study of the 2014 Ludian 6.5 earthquake. I'm going to share our research along the following lines. Groundwater is sensitive to seismic and tectonic activity. Continuous response of well water levels, pre-seismic and co-seismic, provides further evidence for the relationship between seismic activities and changes in water level. However, quantitatively analyzes factors such as crustal stress variations, aquifer deformation, pore pressure changes, and dynamic fluctuations in well water levels from seismic genesis to seismic rupture presents challenge due to their complex nature. Additionally, research on pre-seismic and coseismic response has been separated temporarily due to different physical mechanisms and research objectives. In this study, pre-seismic and coseismic response are considered as continuous processes that involve a series of physical phenomena, including strain, pore pressure, or water level changes before and during an earthquake event. This study aims to establish quantitative relationships between these response processes and hydrogeological parameters, as well as rock mechanical properties, thereby revealing the underlying physical mechanisms governing the continuous pre- and coseismic response of well water levels. This study examines the continuous well water level response to Ludian 6.5 earthquake, especially focusing on the Huizi well. The Ludian earthquake occurs in the southern region of junction between the Bayan block, the Sichuan-Yunnan block, and the South China block. The epicenter was located near the Baogunao Xiaohe Fault and the Zhaotong Ludian Fault, with a focal depth of approximately 20 kilometers. We went to the site of Huizi Well for investigation in 2022 and obtained well data. The depth of Huizi Well is 1,003.50 meters, with casing extending to 87.8 meters, resulting in water level depths of approximately 30 meters. The groundwater type in Huizi Well is classified as fissured confined water. The high-value anomalies in the water level of Huizi Well demonstrate a significant predictive capability for earthquakes occurring east of Sichuan-Yunnan rhombus block. As summarized in table, based on literature records and field investigation conducted at the Huizi County Seismological Bureau, Huizi Well has shown clear pre- and coseismic response to multi-near-field earthquakes. Regarding to the Ludian earthquake, following the Yunshan earthquake on April 2014, the water level in Huizi Well gradually declined from a high state. On July 21, a sudden turning point was observed, leading to an accelerated rise in water level, which continued until the occurrence of Ludian 6.5 earthquake on August 3. The water level rose continuously by approximately 0.7 meters, with a Pre-Seismic anomaly lasting for 13 days, demonstrating a typical pre-earthquake water level rise. The Ludian earthquake struck at 7 p.m. on August 3, with a sudden water level spike observed at 5 p.m. By 6 a.m. on August 6, the water level stabilized, having risen by 0.33 meters, reflecting a typical Coseismic water level increase. After which the water level gradually decreased, returning to pre-event levels within approximately 50 days and to levels before the onset of anomalies within about 90 days. Now let's discuss the construction of the model. Due to the spatial discrepancies between the regional scale of stream field evaluation and the aquifer well flow scale, to achieve a more precise representation of this process, we separate the construction of two models: the pre-seismic and coseismic pore pressure evaluation numerical model at the regional scale, which is employed to obtain the pore pressure evolution at depths within the aquifer near the fault zone, and the aquifer well water level response numerical model at the local well flow scale. The pore pressure serves as an interface for coupling two models, allowing us to obtain the continuous response of well water level to the pre-seismic and coseismic process. To simplify the calculations, the following fundamental assumptions are made. For example, the fault is treated as a strict slip fault, neglecting the vertical displacement. The geological body is unaffected by external forces prior to the applications of boundary condition loads, with strength beginning from zero. We construct the following conceptual model. The precise strength accumulates from zero, using the GPS velocity field as a reference constraint, decomposed into velocity components applied at the boundary of the solid mechanics from regional stress loading, simulating the accumulation process of pre-seismic stress. During the boundary stress loading, the friction coefficient on the fault plane is relatively high, leading to gradual strain accumulation around the fault. A reduction in the friction coefficient triggers fault slip, simulating the occurrence of an earthquake, with the strain field undergoing rapid adjustments to constrain coseismic slip by fault displacement. Once the fault displacement is achieved, the application of velocity components at the boundaries of solid mechanics ceases. Now we may further analyze the mentioned mathematical model. We sought out the theoretical framework and summarized the above physical process into 4 levels and 3 solving processes of stream field, pore pressure, and water level. The governing equation of solid mechanics can be simplified to the following form to describe the variation of stream field. The governing equation for fluid motion are represented by Darcy's law and the mass continuum equation. The stream values corresponding to the depths of the aquifer are extracted And the pore pressure evaluation of the target aquifer pre-seismic is obtained based on the linear equation between pore pressure and volumetric strain. The pore pressure is solved using a three-dimensional coupled equation set of seepage and deformation with pore pressure and displacement as variables. The Navier-Stokes equation are employed as the flow control equation for the water body in the well. This study employs the multi-physical finite element software console to conduct simulations, achieving fluid-solid coupling in a porous elastic geological body. The assembly model simulations the sliding of the two sides of the fault, and the PDF mathematical models solves the three-dimensional coupled equations of seepage and deformation with pore pressure and displacement as variable, ultimately obtaining the pore pressure evaluation of the target aquifer pre- and coseismic. Finally, by constructing a local well flow model, the response simulation of well water level and changing pore pressure is realized. Now let's explain the process of constructing the numerical model. Firstly, considering the spatial position of whether well relative to the fault, geometric model construction and parameter determination are completed. The aquifer well water level response model is established as a two-dimensional axis-metric model centered on the wellbone. Secondly, the pore pressure evaluation of the aquifer before and during the Ludian earthquake under different parameter scheme is simulated. Using parameter scheme 1 as an example, the excess pore water pressure and negative pore water pressure during the pre-seismic and coseismic phase exhibit a quadrangle distribution. The negative pore water pressure areas are aligned with a proposed rupture surface of the fault corresponding to the tensile strain zones, while the opposite quadrants correspond to the excess pore water pressure zones and the compressive strain zones. The rapid change in pore pressure accumulated near the fault zone pre-seismic is due to the reduction of the friction coefficient to 0.4, leading to fault movement. The negative pore water pressure quickly adjusts while excess more water pressure continues to accumulate with the well suited within a region of excess pore water pressure. Whether well water level was in a slow rising phase before the earthquake, while a rapid increase in water level occurred during the coseismic phase due to the rapid adjustment of stream field. The rising trend before the earthquake is influenced by the friction coefficient, while the amplitude of water level changes and the recovery time during the coseismic phase are significantly affected by the aquifer hydraulic conductivity. So comparative analysis and parameter scheme 2, where the friction coefficient changes in a gradient of 1, 0.8, and 0.4, while the aquifer hydraulic conductivity remains constant at 0.389 meters per day. The continuous response simulation of well water level before and during the earthquake phase well with the measured results. After parameter identification, a comparison of simulated well water level values against measured values for the Huizhou well's response to the Ludian earthquake before and during the event is present in the figure. When comparing the measured water levels with the simulated levels, the trends are generally consistent with a measured pre-earthquake water level increase of 0.3 meters and a Coseismic water levels increase of 0.33 meters, displaying a sawtooth fluctuance pattern. With the measured values being lower than the simulated values. Due to the irreproducibility of actual earthquakes, the validation of Huizhou well water level response to simulation results for the Ludian earthquake before and during the events is conducted from several perspectives. Firstly, using the Coseismic stream field based on the dislocation model to validate the distribution of the numerical magnitude of the stream field in this model. The extremum distributed on both sides of the fault and the extremum order of magnitude being on the order of 10 to the power of -6 as shown in table. It indicates that the Coseismic stream field calculated using Coulomb does not consider flowed solid coupling, resulting a smaller range of extremum absolute values compared to those in this research. Secondly, validating the pre-earthquake and Coseismic water level trends using other observation wells near the fault. The Zhaotong well and Zhaoyang well, which are located within the static stream field of the Ludian earthquake, and exhibit significant Coseismic response. Both the Zhaotong well and Zhaoyang well are located within the excess pore water pressure zone before and during the earthquake. Furthermore, due to Coseismic adjustment, the compressive strain values in the areas surrounding these two wells rapidly increase. The measured water level data from both wells show an upward trend before and during the earthquake, corresponding well with the simulated results of the pre- and Coseismic pore pressure field adjustments. In conclusion, we have developed a novel two-part numerical framework that successfully simulates the continuous pre- and Coseismic water level response as a single integrated process. This model has also been applied in other regions in China, for example, Shuangqiao well to Tangshan earthquake. It has achieved the desired result. This work moves us from qualitative observation to quantitative physics-based analysis. It allows us to use water level data to inversely estimate crucial in situ parameters like fault friction properties and aquifer hydraulics. This has significant practical implications for earthquake monitoring, bringing us a step closer to developing physically meaningful processors for earthquake forecasting. Of course, our model is a simplification. The main limit is the separation between the pore pressure and well response models. Our further work will focus on developing a fully integrated three-dimension coupled model that seamlessly connects the strain, pore pressure, and water level processes across all scales, from the fault zone directly to the well screen. Okay, that's all. Thank you for your attention. If you have any questions or need further discussion, please contact me by email.